Hello everyone, welcome to the 15th episode of the series. In this video, I'll talk about eigenvalues and eigenvectors. So I'll start this episode by a motivating question. So if you have a matrix A, is it possible for us to find a vector such that A times the vector X is just X? In other words, can you find a vector X that remains unchanged upon multiplication by A? Uh, if it does exist, we call that vector a fixed vector of the matrix A. So let's see an exercise first. We're given this 3 by 3 matrix with entries 2, 0, 0, 1, 2, minus 1, 1, 3, minus 2, and we want to find vectors uh, that are fixed. So to do that, we're going to write this matrix equation more explicitly. We're going to write this vector of variables as x, y, and z. Uh, so this matrix equation now corresponds to a linear system given by these three equations. And I can take the x, y, and z onto the right-hand side. So first, the first equation gives us that 2x is equal to x. That is, x has to be 0. So we can take this value of x equal to 0 and substitute it in a second or the third equation, and in either case we end up getting that y is equal to z. In that scenario, we let y to be t. Remember that t is a parameter. By the condition y equal to z, we get z is t as well. Therefore, for any t, the vector given by 0 t t is going to be a fixed vector of the matrix A. And we can generalize this problem by including a scaling factor. This is what I mean by a scaling factor. In the previous problem, we wanted ax to be the same as x, or in other words, 1 time x. So essentially, the action of A was to multiply the vector x by the scalar 1. But instead of having that scalar 1, we could have some other number lambda. So it generalizes the problem to this. So these questions that we saw lead to one of the fundamental ideas of this class. And the idea is of eigenvectors, and related to that, we have the idea of eigenvalues. So an eigenvector of a matrix A is a non-zero vector V, such that A times V is lambda times V, where lambda is some scalar. The number lambda is called the eigenvalue of the eigenvector V. And we can also refer to, uh, you know, an eigenvector V with eigenvalue lambda as a lambda eigenvector. For example, in the first exercise, we saw that any vector of the form 0 tt was a fixed vector. Therefore, it was an eigenvector with eigenvalue 1. So 0, 1, 1 is an eigenvector with eigenvalue 1. In a similar fashion, if we were to uh, uh, you know, multiply the matrix A with the vector 1, 1, 1, we see that we end up getting 2, 2, 2, which is 2 times 1, 1, 1. So the vector 1, 1, 1 is also an eigenvector of the matrix A, but for eigenvalue 2. So note that the 0 vector is not an eigenvector of any matrix just by definition, but the eigenvalue can be 0 or non-zero. Okay, so to find eigenvectors, if we are given an eigenvalue, we use this condition, and this is just the condition a v equal to lambda v rewritten. So we've just taken lambda times v to the left hand side and written lambda as lambda times identity. So the problem of finding eigenvectors of a matrix given one of its eigenvalues boils down to finding non-zero solutions to this homogeneous equation. So let's look at an exercise for the sake of clarity. So we're given a 2 by 2 matrix with entries 4, minus 2, minus 2, 1. First, we want to find all the eigenvectors of A with eigenvalue 0, and then we want to find one eigenvector of A with eigenvalue 5. So we set up the equation. A minus lambda times identity is going to be the matrix A minus lambda times identity, of course, and the vector V can just be replaced by the vector of variables x and y, and we set it equal to the 0 vector. Now this A minus lambda I can be simplified to to be written as a single matrix with entries 4 minus lambda, minus 2, minus 2, and 1 minus lambda. So if lambda is 0, then the matrix simplifies to 4 minus 0, minus 2, minus 2, 1 minus 0, and this represents a linear system given by 4x minus 2y equal to 0 and minus 2x plus y equal to 0. To get to this linear system, we just multiply this matrix with this vector xy. Now, since both of these equations are multiples of one another, the first equation here is minus 2 times the second equation. The solutions can be found by declaring x equal to the parameter t, and that just gives us y equal to t, and therefore any vector of the form t comma 2t, where t is a real number, is an eigenvector of the matrix A corresponding to eigenvalue 0. Now, if our eigenvalue was 5, then we replace every instance of lambda with a 5, so we get 4 minus 5, minus 2, minus 2, 1 minus 5, and then there is a linear system corresponding to this matrix equation given by minus x minus 2y equal to 0 and minus 2x minus 4y equal to 0. Now, like before, the second equation is a multiple of the first one, so we can we can find all the solutions by declaring y equal to a parameter t, and that just gives us that x is equal to minus 2t, and therefore any vector v of the form minus 2t t, where t is any real parameter value, is an eigenvector corresponding to eigenvalue 5. Okay, so the last thing I want to mention is that a matrix is only going to have eigenvectors for a very few eigenvalues. It doesn't work for every possible number. And before I end this video, I just want to ask you, how would you find eigenvectors if the matrix was not square? Or does it need to be square so that it can have eigenvectors? And with this, I would like to end this episode. I will see you guys soon. Until then, happy learning.